Good morning, students. Last lecture we see superposition theorem and Thevenin's theorem. Now we have to see Norton's theorem. Okay. In this Norton's theorem, for current analysis, Norton's theorem can be used to reduce a network to simple parallel circuit with a current source. Means in here we see the voltage source, voltage voltage management. Here we have to see the current analysis. Okay, so Norton's theorem can be used to reduce a network to a simple parallel circuit with a current source. Okay, how it states, let's see. Norton's theorem states that the entire network connected to terminals A and B can be replaced by a single current source IN in parallel with a single resistance Rn. In Thevenin's theorem, we see we can replace the single voltage source series with the resistance. In Norton's theorem, we can see Norton's theorem what states that entire network connected to terminal A and B can be replaced by single current source IN in parallel with a resistance. Here the diagram, this is the network, this is the terminal A and B, positive negative. So how it converts, this is the current source IN, and in this with parallel to Rn, these are the two terminals A and B, Norton's equivalent circuit. Okay, understand? In Thevenin's theorem, we have to replace voltage. Here we have to replace the current source. Okay, so here is the current source and the resistance is with parallel to it. Okay, we have to see application of this. Okay, using Norton's theorem, find load current and load voltage in the following circuit. Okay, let's see. Here is the voltage source, one resistors R1, R2 and the load resistance. Okay, what is the first step? Imagine a short circuit across terminals A, B as shown in the figure here. This is the short circuit. Okay, next what? This short circuit RL and these short circuits RL and the parallel R2. Here the R2 and RL are parallel. Okay. Next, the only resistance in the circuit is R1. Okay. These are grounded. These are grounded. Therefore, the resistance is only R1 in series with what? Voltage source. Okay, the short circuit current, therefore current is how flowing is in this resistance. Therefore IN equal to 20 volt V divided by R. 20 volt divided by R equal to what? 5 ampere. Okay, understand? Next what? Second step, to find Rn, to find the Rn means what? Short circuit resistance. To find Norton's resistance, remove the short circuit across AB and consider these terminals open. Okay, now remove this short circuit AB is open without RL with no load resistance. Now the source voltage is considered to be short circuited. Okay, this is the voltage source, RL is removed and this will be open. Therefore R1 is in parallel with R2. Here this R1 is parallel with R2. Okay, next what? Therefore Rn, we have to calculate what? Rn, R1 R2 divided by R1 plus R2. R1 into R2 divided by R1 plus R2 equal to what? R1 is 4 and R2 is 6. You have to calculate the Rn. Okay, 2.4 ohm. Okay, how Rn is calculated? Remove short circuit across AB. Okay, remove short circuit and with no load resistance. We don't want to connect the load resistance. Okay, then this is the R1 and R2 in series. Okay, therefore R1 and R2 is in parallel. Okay, so we have to calculate Rn. Then we see the Norton's equivalent circuit. IN we calculated here, and this is RN. So IN 5 ampere and RN 2.4 ohm. Okay. The arrow on the current source shows the direction of electron flow from B to A. B to A. This is okay. Next what? To calculate IL means load current, replace RL between terminal A and B. Here we have to connect the RL. If current through RN is I1 and current through RL is IL, then IL is what? IL equal to IN. We have to know IN. RN divided by RN plus RL. Okay, so IN we know 5 ampere and we know the RN also and RL also. So VL equal to so IL equal to what? 2.222 volt, and VL means V equal to IR. So we have to calculate load voltage. So this is 6.6 volt, 6.66 volt. Okay, understand? This is the Norton's theorem. We have to connect current source is parallel with the resistance RN. Means IN is equal to what? Norton's current equivalent, and RN is Norton's resistance. Okay, fine. So next we have to see Thevenin's Norton's conversion. Okay, it is possible to convert directly from Thevenin form to a Norton form and vice versa. The following formulae can be used for this conversion. Okay, Thevenin from Norton. Okay, RTH equal to RN. This is the resistance of Thevenin. This is the resistance for RN, and VTH equal to IN into RN. So Thevenin's voltage equal to what? Norton's current and Norton's resistance. This is for Thevenin's from to Norton's from. Ulta, Norton from Thevenin's. What? RN is equal to RTH. So IN equal to VTH divided by RTH. Okay. So here VTH and VRTH is given. We have to convert it for IN source and RN source. This RTH and RN are the same. Okay, fine. Next we have to see maximum power transfer theorem. Let's consider a source such as battery or DC generator having an EMF E and an internal resistance R as shown in the dotted rectangle. Here is the EMF, or this is the resistance R. Okay, a variable resistor is connected across terminals A and B. This is the variable resistors, mean load resistors across A and B. If the value of load resistance is RL, the value of load resistance is RL, then what is formula given? I equal to E means here the voltage EMF divided by this small r plus RL. Small r plus RL. Okay. Power transferred to the load. I square R. What is the power formula? I square R. This power is maximum when RL is equal to R. How this power is maximum? When RL is equal to this series R, small r resistance. Okay. So what? Maximum power transfer theorem states that the power transferred from the source to the load is maximum when the resistance of a load is equal to the internal resistance of a source. How? This is the source. We have to connect the voltage source and the series resistance R and the load resistance R. This is the variable resistance. When the load resistance and the small r internal resistance are equal, then this circuit gives the maximum power. And what is the maximum power formula? I square R. Okay, understand? This condition is called resistance matching condition. Okay. Resistance matching is important in communication and electronic circuits where the source usually has a relatively high resistance and where it is desired to transfer the largest possible amount of power from the source to the load. When or in DC generators and secondary batteries. The internal resistance is low. Therefore, it is impossible to satisfy this condition without overloading the source. Okay, understand maximum power transfer theorem. Thank you.